Hello, Dr. Nat here. So we are doing chapter 15 part 2, which is on the kinetic theory of gases. Previously in part 1, we talked about the beautiful equation of PV equals to nRT. I'm calling it beautiful if you're not. So PV equals to nRT can be used for ideal gases and for gases that can be approximated as ideal gases, such as gases with low density. Okay. Now, N. What is N? We talked about this. N is the number of moles of gas, right? This guy is moles. And in chemistry, they teach you N is equal to capital N over capital N subscript A. So what is that? N is the number of molecules in a container or whatever system that you have. Can be either a piston, whatever object that you fill in the gas, molecules in a container, and Na is the Avogadro constant. It's not the avocado, it's Avogadro. Okay, Avogadro. Okay, Avogadro's constant, which is 6.02 times 10 to the 23 particles or molecules. And this is per mole. Per mole, which means that when you divide molecules over molecules or particles over particles, you are left with only the mole because these guys cancel out. Okay, they cancel out. So you are left with moles. So this equation, you should have learned it in chemistry. Why is it important here? Now I can write this equation to be capital N over NA RT equals to PV. Okay, that was anticlimax, but it is equal to PV. Okay, so why is this important? Another constant. Previously, we talked about R, which is the universal gas constant. This guy is the universal gas constant. If I were to factor out R over NA, when I factor out both constants, R is a constant, Na is also a constant, it's Avogadro constant, I say this is actually K. Sorry, it's a small k. Teeny weeny k. Okay, it's a small k. This k can either be a small k or a k with a subscript B. It is known as the Boltzmann constant. I know, another constant. This is your third constant in this chapter. Anyway, previously, we started with R equals to universal gas constant. Now we have another constant, which is actually a constant over a constant. R over Na is the Boltzmann constant. Now I can rewrite this equation to be... Okay, just ignore the screaming in the background for now. I'm gonna explain what's going on. Well, maybe I won't explain, who knows. Okay, so now I want to use K in my equation. So how does it look like? And PV equals to N small k and KT. So this is my ideal gas equation, but using the K constant. It can also be PV equals to small n RT. Okay? Okay, so now we go into the kinetic energy theory. When we look at gas moving randomly, there's movement involved, right? Which means that there is some kind of kinetic energy because there's movement. Okay, so how do we relate gas to kinetic energy? So kinetic energy is 1 over 2 mv squared. Now, we are taking the average velocity of these molecules or these particles. So I'm going to put average here. So this is 1 over 2 mv average squared because this is the V average of all the particles or all the molecules in the gas system. Okay, so I'm not going to tell you how this is derived, but 1 over 2 mv squared is equal to 3 over 2 small k Boltzmann constant times temperature. So this is the equation. So the kinetic energy is related to gas, right? Why is it related to gas? Because Kb is R over Na. and R is a universal gas constant. So basically we are relating it to gas. So this is the equation. Okay, now if this guy is our average kinetic energy for the molecule inside the gas system, what is the total kinetic energy? I can say that the total kinetic energy for a gas system is the number of molecules times with 1/2 mv average squared, which means that I can also say that this equation is equal to 3/2 n kT, right? Okay, what next? I don't want to make your life harder, but in this case it's necessary. So this guy can also be converted to the RT equation, right? Because KB is equal to R over NA. So I can rewrite this to be 3/2 N over NA RT. Does this look familiar? It should be, because I just talked about it like a few minutes ago. So this is 3/2 N RT, which gives us the total kinetic energy. Wow. Total KE. Okay, so this is total KE. For a monoatomic gas, the kinetic energy is pretty simple, and it is described exactly by this equation. So the internal energy for a internal energy for a monoatomic gas. Am I spelling this right? I hope so. Monoatomic gas is equal to the total KE, which is equal to 3/2 nRT. Internal energy can be written as U. Internal energy for monoatomic gas. Okay, so that is U. This is how we get the 3/2 nRT. Okay. And again, I don't want to make your life harder, but in this case, I have to. Average has the same meaning as mean, right? Average is mean, purata, right? Purata. So, if you come across a problem that asks you, what is the root mean square velocity of these molecules, right? We have the equation, we have the velocity squared, we have the velocity in mean, which is the average. It wants us to know what is the V root mean square. So what do? I just say, okay, I can do that. So 3/2 kBT times with 2 divided by m, and this guy is average squared, and I want to square this guy. So if I were to square this guy, I have to square everyone. Squaring everyone. So this guy becomes the VRMS, and this guy becomes 2 cancels out, 3/mkt squared. So this is your root mean square velocity for the molecules in your gas system. What does this equation tells us really? Okay, let's look at it. So m, this is the mass, right? The mass of the molecule. So if I am a heavy molecule, yeah, because I'm curvy, I am a heavy molecule, which means that m is great, m is a high value, which means that my V will become slower. If I am a heavy molecule, my speed will become slower. If I am a lighter molecule, in terms of mass, my speed will be higher. Okay, if I am not heavy, my mass is small, my V will increase. Okay, so that's one thing that this equation can tell you. What else? Vrms is also equal to T. If my temperature is high, what happens? If my temperature of the gas is high, my Vrms will increase. Let's use a different color for that. Let's use blue, okay? So blue. If my temperature is high, my V also has to be high. So here we can say that Vrms is proportional to the temperature of the gas system, and Vrms is inversely proportional to the weight, to the mass of the molecule. So lagi berat, lagi slow. Lagi tinggi temperature, lagi laju. So this is what this equation tells us. Alright, so that's the end of kinetic theory. Bye-bye.